So in this video, we're going to take a quick look at cis and trans isomerism in alkenes. This is a type of geometric isomerism, and we've seen it before. We saw it in cycloalkanes. You had a ring of carbon atoms, and that had two branches on different carbons in the ring. We noticed that those two branches could be on the same side of the ring, and we called that the cis isomer, or the two branches could have been on opposite sides of the ring. One could have been above the ring, the other one below the ring. In that case, it was called a trans isomer. The same phenomenon occurs with some, but not all, alkenes. So we're going to try to figure out when it occurs, and if it does occur, which version do we have, the cis or trans isomer? To start us off, let's look at this example here. So you notice it is an alkene because it has a double bond. Well, look at the two carbons in the double bond. There they are. This is a bond line formula. It doesn't show most of the carbons or hydrogens. Usually it doesn't show any of them, but this one shows terminal carbons with hydrogens. If I show the carbons, we know there's two carbons here, and since carbon needs 4 bonds, we know that they each have a hydrogen attached as well. All right, so one other feature to remember is with alkenes, the bond angles are 120 degrees, which means in this situation, you'll have a hydrogen coming up above the double bond, and then you have another bond going below the double bond. On the left side, a hydrogen coming down below the double bond, and a methyl group coming up above the double bond. That bond angle is what makes that happen. Now, if you look at the two carbons in the ring, in the double bond, notice that each of them has two different things attached. We can say they have two different substituents. Okay, that's a fancy way of saying substituents. Two different things attached. That's what substituents are, things that are attached. The carbon on the left of the double bond has a methyl group. I didn't mean to erase that. It has a methyl group and it has a hydrogen atom attached. Two different things. The carbon on the right side of the double bond has a hydrogen attached and it has an ethyl group attached. Two different things. So that's what you want to notice. If the carbons in the double bond, each of them have two different things attached, like we see here, then cis and trans isomerism will exist. So let me say that again. If the two carbons in that double bond, each of them have two different things attached, then yes, there will be cis and trans isomerism. So let's look more closely. Let me stop highlighting crazily and erase all that. If we look at those two carbons in the double bond, we notice that the methyl group up here is coming above the double bond, while the ethyl group down here is coming below the double bond. They're on opposite sides of the double bond. Because they're on opposite sides, this is going to be a trans isomer. The name of this molecule, with 1, 2, 3, 4, 5 carbons in its chain, would be trans pent 2, 2-ene. It's the trans isomer because the methyl group is above that double bond while the ethyl group is below. Now you might be asking a couple of good questions. Why did I focus on those? Remember, there were hydrogens here as well. I focused on the carbons because they're higher priority than hydrogens. So I noticed the hydrogens simply to say to myself, there is cis or trans isomerism because each carbon had two different things attached. So I wanted to notice the hydrogens were there. However, once I've established that there is cis and trans isomerism, then I ignored the hydrogens and I just looked at the carbon groups that were on the two sides of the double bond. The second thing you might wonder is, why does this matter? Like, why is there trans isomerism? Couldn't we just rotate this and have the ethyl group move up instead of down? Or couldn't we rotate it and move the methyl group down instead of up? The answer is no. If you play with the model sets in the lab, you'll notice that wherever you have a single bond, so this bond, or this bond, or any of the carbon-hydrogen bonds, when they're single bonds, you can easily and fully rotate those things. So on the ethyl group, I've shown that there's this bond here comes down to the left. Well, if I wanted, I could rotate it and have it come down over here instead. That's because those are single bonds. We can easily rotate them. But the double bond here in the middle prevents rotation. That second bond in the double bond stops you from rotating it in the same way that a ring stops you from rotating. Because we can no longer rotate around that double bond, the methyl group here and the ethyl group here will always be on opposite sides of the double bond. That's why it's a trans isomer. If we had drawn the same molecule, pent-2-ene, but I had drawn the methyl group here going up, and I had drawn the ethyl group also going up, now the two groups, the two carbon groups, are on the same side of the double bond. They happen to both be going up. They could also have both been coming down. It wouldn't matter. If they're on the same side of the double bond, that instead of a trans isomer, we would have had a cis isomer. We would have called the molecule on the right cis-pent-2-ene. Take a look at this molecule and decide, does it have cis or trans isomerism? You see the two carbons in the double bond, and you notice that each of them, if I show their hydrogens, normally you would just imagine this. If you look at the hydrogens, you'll notice that the carbon on the left has two different things attached. The carbon on the right of the double bond also has two different things attached. Because they each have two different things attached, yes, this will have cis and trans isomerism. So now, which is it? Is this the cis isomer or is it the trans isomer? So look at your double bond and look at those carbon groups that are attached. The methyl group is up and to the left, it's above the double bond, but the carbon below and the entire group there is coming down below the double bond. So those are on opposite sides of the double bond. So this would be a trans isomer. Its full name, if you want to pause and try to finish the name, its full name would be trans 1, 2, 3, 4. So I keep changing my pen. Trans 4-methyl and then pent-2-ene. That would be its full name. Try another example here. Pause the video. Does it have cis or trans isomerism? And if it does, which is it? So we look at the two carbons in the double bond. I know that each of them has a hydrogen attached. Normally, you just imagine that. You don't draw it like this. So if I look at the carbon up here, it has two different things attached, the hydrogen and the methyl. If I look at the carbon on the other side of the double bond, it also has two different things attached. So yes, this will have cis and trans isomerism. So which one is it? Well, the methyl group is coming up on one side of the double bond, And this carbon group is coming up on the same side. They're both on that side of the double bond. Since they're on the same side, this is the cis isomer. Pause the video and come up with its full name. So the parent chain has 1, 2, 3, 4, 5, 6, 7 carbons. There's an ethyl branch on the 4th carbon. There's a methyl branch on the 5th carbon. So the name would be cis 4-ethyl. We put that first because it's alphabetical. And then we say 5-methyl. And then we'll say hept. And it's the second bond, so hept-2-ene. So there's the full name. Let's do one more example. Let me find a different example here. What about this guy here? Does it have cis or trans isomerism? Pause the video and decide. So the 2 carbons in the double bond are there. And I noticed immediately that the carbon on the left has 2 identical groups attached. It's got 2 methyl groups. As soon as I noticed that it does not have 2 different things attached, then I realized this will not have cis or trans isomerism. Why not? Well, a simple way to understand why not is imagine taking those 2 groups and switching them. Trade places. Because they're identical, trading places will not in any way change the molecule. So therefore, it will not have a cis or trans geometry. If you look back at one of our cis or trans examples, like this one, remember there was a hydrogen here. If you were to take this hydrogen and this methyl group and switch places, then yes, this would change the shape of the molecule. In fact, it would change it from the trans isomer that we see here to the cis isomer. You have to have 2 different things attached on both sides of the double bond for that to happen. If you have the same things attached to even just one of the carbons like we see here, then when you trade places with those 2 methyl groups, if you switch them, the molecule won't change. So therefore, this has no cis or trans isomerism. Its name, you can pause the video and come up with it. It's going to be 2-methyl but-2-ene. We don't put a cis or trans prefix because it doesn't exist here. So I hope that helps with cis and trans isomerism in alkenes.